Focus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stuart Chaffee, and this is Gary Kildall. Gary, I've been working with this abacus here, and the abacus is, of course, one of the oldest computing machines, about 5,000 years old, and if you're really fast, maybe you can do 2 or 3 operations per second on this thing. Well, today, of course, we're talking about computers which can do hundreds of millions of operations per second. The question is, why do you need that incredible kind of speed in a computer?
Well, incredible speed helps sell computers, for one thing. But realistically, there are many problems that do require high-performance computers to get an effective solution. Real-time graphics is one example where the foreground and background images change at a fixed rate of, say, 30 frames per second. It takes a higher performance processor to keep up with a higher density graphics to match that frame rate. Now, there are many examples like that. Say, weather modeling is one. Another is the information analysis required by an expert system.
Okay, these incredibly fast computers are called supercomputers, and that's the subject of our program today. We'll see the fastest computers in the world in operation, both here in the United States and in Japan. Let's begin our look at supercomputers by seeing what's going on in this country.
Over 1 million times faster than the serial processing machines of the 1950s, modern supercomputers owe most of their high-speed capabilities to massive parallel architectures. Multiple functional units and comprehensive pipelining have led to processing speeds in excess of 100 million operations per second. Supercomputer applications are as distinctly varied as they are specialized, from satellite imagery to superreal graphics, from space exploration to doomsday weapons research. At Lawrence Livermore Laboratory, the world's largest user of supercomputers, magnetic fusion experiments require massive computing power available through the lab's Octopus network, a multi-access system that shares a total of 7 supercomputers. Processing time on these machines is rented to over 150 American and foreign users who gain access through satellite transmission. But the fastest machine at the lab, and one of the fastest commercially available, is the Cray XMP. This dual-processor supercomputer is reserved for the most secretive and the most costly activity at Lawrence, nuclear weapons design and analysis. With the Japanese now challenging what was once an American-dominated market, supercomputer research is taking on a new approach. The Japanese machines are not only faster, but they offer simpler, more portable software that uses standard programs aimed at a much wider market. Like the extremely successful bullet train, Japan's supercomputers herald a new generation of speed and technical sophistication. At issue is whether American companies will play a role in this new era of super-fast computers.
Joining us now is George Michael. George is head of the Computing Research Group at Lawrence Livermore National Laboratory, and John Repp, Marketing Program Manager for Control Data Corporation. Gary?
George, it was about 10 years ago that I sold one of the first CPM systems in Lawrence Livermore Labs, and it was used as a little peripheral on the Octopus network, a network of supercomputers with microfiche storage and so forth. What was going on out there? What goes on at Livermore Labs with supercomputers?
Well, the business of the laboratory is solving partial differential equations when it comes right down to it. Okay? They're doing advanced technological stuff in where it's based on nuclear energy or weapon technology, anything like that. These things require enormous computations. Okay? You'd like to be sure that you're right. So we use computers to do that. In other words, a computer is not an end in itself, it's the thing that's used to support the work that the laboratory is chartered to do.
Do you find that what you do is you buy more and more computers as your need grows, or you try to use different techniques to use those computers more effectively?
Oh,
What's
we do
the process?
Both. We do both. Mm-hmm. In fact, the secret to supercomputers or to any other computer at any time in any context is that it's more than just a computer. There has to be a language to express ideas. There has to be algorithm development that shows how to be sure you've done the right thing. Okay. Given that, it's Well, there's a lot of research that has to go on that prevents you from just saying, I can buy that computer and just get another factor of 20 or whatever it is that you need in speed. You have to build the thing in, as you well know.
Now, you work a lot with Controlled Data Corporation, is that correct? And with
Yes,
John.
we do.
And what is it in the technology now? What are the limitations? Do we really have our supercomputers growing in order of magnitude every few years, or what's going on?
Well, I don't know. I don't know how John feels about it, but I will say that if you plot the performance characteristic of machines since 1950, what you can see is that there's been a 2 orders of magnitude, that's a factor of 100, improvement in the decade from 50 to 60 and from 60 to 70, and then it turned over and we didn't get a factor of 10. Why? Well, some of the stuff was that the components are tired or they just can't go any faster. Some of the things is that we're trying to do things incorrectly. Okay, we got to rethink about how they're done, and some of it was that the machines require very strange perturbations in algorithms before they'll really perform. So we have to change all that and bring it all together, and then we'll start picking up speed again.
Now, the CDC Star was I guess a supercomputer, what, 10 years ago, and it was a different architecture, and it was basically an array processing machine. And one of the difficulties that came about with the Star was that it really required different kinds of compilers and software techniques. Has that been a problem over the last 10 years? Has it been solved?
Well, when Star was first introduced, I think part of it with the help of the laboratories and coming up with a new philosophy, a new logic to produce the high power, you restructure your whole problem, restructure your thinking and how you were going to solve a problem. And over the years, it's taken quite some time to get to the point where vectors are recognized. I deal primarily in the commercial world, and as George and I were talking beforehand, the evolution was in the government. The government had the R&D funds. The government was able to produce and use the kind of architecture that came up. And we're seeing in the commercial world, it's almost a revolution right now. We were talking about, it's kind of like jumping on the bandwagon now of, I got to have one. I ought to get to a point where I can use it. And they're also reaching a point where they can't solve the problems in the same old way they were doing it. They went into the three-dimensional world where you have a lot more data points that you have to analyze and through whatever algorithms, and they're reaching a point where they could keep adding a lot of computers, or they could go to what we quote-unquote call a supercomputer today and move into tomorrow. So we're seeing quite a bit of change going on right now.
John, what are the commercial applications? We've heard about Lawrence Livermore and those kind of research and government things. What are the commercial applications now of a supercomputer?
Well, I can let me categorize it a touch into 3 or 4 different areas. Petroleum. Petroleum companies or oil companies have gone into supercomputing in a big way, not still totally knowing what they're doing with it, but the search for oil. Again, domestically, they've had to take a look at the seismic processing and also the reservoir simulation. So that's been a very big move, and probably the biggest, as far as I know, in usage of supercomputers. But again, restructuring the way they do things. It's a three-dimensional world, again, that they're looking at. In the automobile industry, we're starting to see that the major companies in the U.S. are going to supercomputing. They want to be able to crash a car by a computer versus taking a number of cars and smashing them up the way they have. They look at productivity of number of cars they have to produce to make a profit. And several of the companies now, by using larger computers and going into supercomputing, have been able to cut the number of cars that they produce to become profitable. And again, that's computer-aided design and all the things they're doing.
One of the things that Captain Grace Hopper used to hand out at her lecture is the Grace Hopper nanosecond, which is about this long, and the distance that light travels in a nanosecond. She claimed that this is a fundamental limitation to the speed of computing, and what's your feeling on that? Has that been solved by various techniques? But
I don't think it's a limit. In fact, I've not seen any physical quantity an effective limit. You tell me about the limit or tell the research world about it, and they'll figure a way around it. Parallelism is a simple-minded way of getting around the limit of how much signal can travel in a given unit of time. Parallelism is a radically new idea, and yet it's very, very old. But in order to successfully cope with it, as John says, there's a great deal of rethinking that has to be done. And perhaps it's the most difficult part that we face right now. Okay, we have to do it in such a way that the ultimate user isn't besotted with all this stuff that, in minutiae that ruins him. And he can concentrate on his problem. But we have to take care that when his program is running on a machine, that it will run correctly and it will complete its job and things like that. That's something that people are just beginning to study now, Well, I shouldn't say just beginning to study. Maybe the last 10 years people have been looking at that. The intensity of that kind of study is increasing right now.
George, you've mentioned you kind of hit a wall this decade and not continuing to increase the speed. What are the technological problems? What are the barriers? I mean, what are the areas in which research is being focused to continue to increase speed?
Okay, let's take the star as the first example. When the star is going to perform at its, quote, blazingly high speed, okay, the vector unit, which is part of the machine, must be running, okay? As far as the scientific computations are concerned, it turns out that a great deal of the computation cannot be kept in the vector mode, okay? It drops out of it. We call that entering a scalar mode, and then when if the scalar is slow, well, you just go slower, okay? Now, it was a traumatic experience to learn how to vectorize big physics codes, you know, things that are concerned with the flow of fluid or concerned with the migration of neutrons all over a reactor or something like that. Okay? It was tough to do that. So we had to invent vectorizing compilers, and then we learned that it's easy to get 60% of the overall program to vectorize, but then the other 40% will be the dominant thing in terms of how you perceive its speed. That's the...
So you feel like the real problem right now is mainly trying to rethink how the algorithms are stated and presented to the computer system rather than trying to change the underlying technology itself.
Well, there's some importance, excuse me, John, there is some importance in getting better technology, but in fact, that's just what you've said is the major problem. We have to learn how to, in a sense, remap algorithms onto architectures, and I feel that it's time to challenge the manufacturers in some sense and say, instead of us having to warp our algorithms to fit your computers, why don't you learn how to warp your computer to fit my algorithm? And so we're getting a little dialogue going, and we're introducing the universities to that dialogue too. And I think that's going to lead, before the end of this decade, to some really successful stuff.
John, what's your response?
Well, I was going to say I don't disagree. It's just if you take a look at the commercial world, and instead of rewriting their codes, they've done conversions. And they've taken a real cut at making conversions, and obviously they're not using the supercomputer the way it can be done. It's in a lot of cases, very time-consuming and expensive. And they have a lot of code that they've written over the years, and it's all been built on and changed and added to. And to go rewrite, to do vector coding, to go on and do pure, solid vector coding, it takes a lot of time to rethink the problem.
It's the redevelopment of all those programs.
As a matter of fact, in one case that I've seen this done, they've gotten spectacular results. But it took time and a lot of R&D on their part to do it.
Okay, in just a moment, we're going to go to Japan to look at the Japanese version of a supercomputer. That's coming up next.
At the University of Tokyo, the Computer Science Department has a new Hitachi model S01E24, one of the fastest supercomputers in the world, capable of 800 million floating-point operations per second. Hitachi Corporation is one of the 10 participants in the National Super Speed Computer Project, a long-term collaboration between the Japanese public and private sectors, aimed at producing a supercomputer 10 times faster than the fastest known today, one that is capable of 10 billion flops per second.
私が作ろうとしているスーパーコンピューターというのは
The computer we are planning to build will be 10 times faster because of its chip design.
一桁速いもの。で、アーキテクチ
The
ャで
architecture will have to be 100 times faster to achieve a tenfold increase in
を
speed.
作りたいと。で、したがってデバイスではジョセフソン・ジャンクションとハイエレ
The
クトロンモビリテ
technology
ィトラ
we are
ンジスタ
exploring to reach this speed includes Josephson junctions, high electron mobility transistors, and gallium arsenide.
それからそのアーキテクチャの方
In
では
terms of architecture, we will have to develop a much higher degree of parallel processing.
処理する方法というのを追求しようと。
We are also working on new software suitable for this kind of architecture.
The testing of superconductive materials and new chip designs is underway at the government's electrotechnical laboratory, part of a massive scientific and academic complex in Tsukuba, also known as Science City, about 60 miles north of Tokyo. Because of the extreme heat created by high-speed circuitry, chips must be cooled to extreme temperatures. In this test, an experimental chip is immersed in liquid nitrogen. Its functional operating temperature is minus 270 degrees centigrade. In tests like this one on Josephson's junction switches, the laboratory has achieved higher speeds than with gallium arsenide. Higher computational speed will also depend on new ways of handling data through parallel processing and pipeline architecture.
一方、一つはね、ベルトコンベヤーをお考えいただきゃいいと思います。
The best way to explain parallel processing and multi-pipeline architecture is by comparing it to an auto assembly line conveyor belt. The belt begins with one part and picks up components along the way until the product is complete. It's an efficient way to make one product using one line. Now, if you increase the number of conveyor belts, you can produce more cars. But if you increase the number of belts by 100, for example, don't expect to increase the output by 100 times, because to allocate work to 100 conveyor belts efficiently is very difficult. You need a good manager to allocate parts effectively. On the other hand, while we can't expect 100 times the output with 100 times as many processors, we can still expect a substantial increase in processing capacity.
The comprehensive Japanese approach to high-speed computation has led to some impressive accomplishments and some lingering uncertainties.
Joseph's junction should be used in a very low temperature. So if we move it from the low temperature to the room temperature, it will be breakdown. It seems to be very difficult to extend them to large-scale computer logic with high reliability for practical use.
One of our problems is that when we develop a new machine, we need a new language. Since most research centers at present have a great number of Fortran programs, our success with the machine depends in part on whether users are willing to change to a new language. Some new languages have been developed, but very few are in widespread use today. It could become a very big problem.
The supercomputer project's merger of private and public sectors results in some unusual arrangements between the companies and the government labs.
Patent or copyright which are developed during the joint project period, those patents should belong to the nation, in other words, Japan government. However, the participant has the right to use such a patent. And second problem is after finishing the project, each makers, in other words, participant, develops the own products. At that time, in other words, we are completely free competition.
Directors of the multi-million-dollar supercomputer project don't see it as a threat to monopolize the world market, but as an efficient way to make major leaps in a field where small breakthroughs can lead to revolutionary changes.
Good technology is always born out of a competitive environment. So if America were the only country developing this kind of computer, we wouldn't expect the kind of breakthroughs that come from competition. Or if Japan monopolized the research, I don't think the progress we're seeing now would continue. We hope that we can always be a good competitor of the United States.
Okay, George and John, there is the perception of a kind of competition between the Japanese computer companies and the American computer companies, Cray and CBC, in the supercomputer field. How do you see is there a difference in approach between the Japanese and the Americans?
I think that you'd have to say there is a difference of approach. I'm not sure that's the place to look for the success that they seem to be enjoying, they have, well, just take the case of Fujitsu. By our discussions with them, they managed to analyze about 5,000 programs, Fortran programs, and then they wrote a vectorizing compiler. And what they learned was partly encapsulated in the compiler and partly introduced in their hardware. So the compiler knows it's got strange kinds of pieces of hardware and it can use them. The effect of that is that we think it's about the best looking compiler we've run into. Now, it doesn't say it's the only good one, but it certainly is good. And as a first approximation, I'm really impressed. I really would worry more about the next generation of computers that comes along from them rather than the current ones. Okay.
John, what's CDC's reaction to what NEC, Hitachi, Fujitsu are doing?
Well, I think we're looking at, first of all, it's not proven. I think they're still in a research environment. They haven't delivered. But let's say they even deliver what they've committed to. I think by 1986, you're going to see the U.S. companies coming out with powers of 10 over what they're producing right now. So where does that take you after 86, 87? I think we're looking at magnitudes of 100 by 1990. So I think we've met the competition pretty well. They've certainly been tough competitors, and they've come up with some excellent technology. But we look at ours being tenfold of that by 1986, 87.
Are there bigger consequences? We hear of, the leadership and defense aspects, George, and who will have the leadership role in either the next generation or supercomputers. Is it really a big issue, this competition?
I think so. I think that well, we're not faced with a life and death situation. I believe that if people in this country don't get busy, that the Japanese machines will become dominant in terms of the speed that they can produce and the price that they can sell it at. We have, to contrast Fujitsu and Hitachi and NEC, we have Cray, CDC, and then it gets hard to find somebody else here. Denelcor is trying mightily, and a few others that are not named that well yet. I mean, they aren't really visible. That's nothing to meet the structured challenge that the Japanese have, if you want to call it a challenge.
Okay, gentlemen, that's all the time we have. Thanks so much for joining us. Thank you for being with us on this edition of the
Creators of visual programming tools for software development is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.